If you're trying to build the holy grail of artificial intelligence.
Which is, a truly autonomous agent.
Right, an agent that can learn about its world without a human constantly holding its hand.
Yeah.
If you try to build that, you eventually run into this really bizarre behavioral problem.
It's incredibly counterintuitive.
Yeah, so say you build this highly sophisticated robotic brain, right? You put it in a physical body, and you place it in a room it has never seen before.
No programmed map.
Exactly. No map. And you aren't giving it points for finding a door or anything like that.
You're just giving it a core mathematical drive to learn.
It's just a drive to learn. And you turn it on. And you step back, expecting it to boldly explore its new environment.
But it doesn't.
No. Instead, the robot immediately walks into the nearest corner, turns its optical sensors toward the blank wall, and just stands there.
Completely paralyzed.
Forever. It just stays there.
Or you run a totally different test. You put a television in the center of the room, and it's playing random static.
Just classic white noise. Right. You power up the robot, and it immediately walks up to the screen, sits down, and just stares at the flashing static. Utterly mesmerized.
And again, it never moves.
Never moves again. And these aren't just like hypothetical glitches, right? These are famous persistent failure modes in AI research. They're actually known as the darkroom problem and the noisy television failure.
Two have been huge roadblocks.
Yeah. And today, we are looking at a brand new state-of-the-art paper that is forming the foundation of modern reinforcement learning because it finally solves these traps.
It's a massive breakthrough.
It really is. Our goal for you today is to extract the mechanics of how we are teaching machines to be genuinely, productively curious. And we're going to do it without needing a PhD in machine learning to understand the math.
Because the underlying tension here is, well, it's one of the most fascinating puzzles in computer science right now.
Totally.
When we talk about unsupervised reinforcement learning, we're really talking about agents that require intrinsic motivation.
Internal drives.
Exactly. I mean, in a standard video game AI, you have an extrinsic reward, right? You get a point for grabbing a coin, or you lose a life for falling in a pit. The goal is entirely external.
The programmer gave it the goal.
Right. But an autonomous agent dropped into the real world, it doesn't have a human scoring its every move.
Yeah.
It has to generate its own internal rewards to figure out what's worth doing.
But historically, we've kind of messed that up.
Oh, completely. The mathematical structures we've used to define those internal rewards, they've basically forced the AI into these rigid, self-defeating behaviors.
Right, because we essentially forced the AI to pre-commit to a single relationship with surprise.
Yes.
And that forced commitment creates two distinct traps. The first one is the trap of surprise minimization.
Which leads to the dark room.
Exactly. If you design an AI that gets an internal reward for making its environment predictable, you end up with systems like smear or all.
Smear or all, yeah. Surprise, minimizing reinforcement learning.
Okay, let's unpack this with a bit of an analogy.
Yeah.
Because it's kind of like a toddler.
Oh, I like that.
If a toddler's core drive is avoiding surprise, they're just going to hide under a blanket forever. That's their dark room. But if their core drive is seeking unpredictability, they'll just stare at a flashing static screen, the noisy TV, instead of actually learning to navigate the real world.
That is a perfect way to visualize it, because you can understand the logic behind SMRL, right? From a survival standpoint, biological organisms generally do want to minimize surprise.
Nobody likes getting jumped.
Exactly. If you're an animal and you suddenly experience a massive spike in unpredictable sensory data, like, say, a predator jumping out of the bushes.
That's a bad day.
That is a highly negative evolutionary state. You want a stable, predictable environment.
Makes sense.
So programmers designed agents that seek to minimize what they call negative self-information.
Right.
Basically, the agent gets a dopamine hit, mathematically speaking, for accurately predicting what's going to happen next.
Yep.
Now, if you drop an agent like this into a chaotic, unstable environment, like a simulated world where the floor is constantly shifting, minimizing surprise actually works really well. The agent learns to navigate the chaos just to find safe, stable ground.
But the moment you take that exact same surprise minimizing agent and drop it into a quiet, completely stable room, the whole logic just collapses on itself.
It completely breaks.
And this is the dark room problem, right? Which Carl Friston conceptualized way back in 2012.
Precisely. Because the AI is constantly running this calculation. It's asking, how can I guarantee that my next sensory input perfectly matches my prediction?
Right.
If it takes a step forward, the lighting might change.
Or the pixel shift.
Yeah, the pixel values of its vision shift.
Yeah.
That introduces variables. It introduces a non-zero chance of being surprised.
And since it hates surprise?
Exactly. The AI quickly deduces that the absolute mathematical optimum for its reward function is to remove all input entirely. So it goes to a dark corner and does nothing.
Because doing nothing guarantees zero surprise.
Zero surprise.
It's literally like putting someone in a sensory deprivation tank. If your only fundamental drive in life is to avoid unpredictable stimuli, the most logical action is to unplug your sensors entirely.
Which is obviously not useful for an AI. We want to actually do things.
Right, so researchers swung the pendulum completely in the other direction.
They did.
They built systems based on prediction error curiosity, which leads us right into this second trap, surprise maximization.
Yeah, they were frustrated by agents hiding in corners, so engineers decided, well, let's just reward the AI for finding things it cannot predict.
So it actively hunts for expected surprise.
Yes. And if you drop this kind of agent into a static, boring maze, it behaves beautifully.
Because everything is new.
Exactly. It explores every single corridor because every new hallway provides a fresh prediction error. It builds a great map of the maze because it's just starved for new data.
Until it encounters something fundamentally random.
And there it is.
This is where the noisy television failure happens. The AI is looking for prediction errors. So if it finds a TV showing pure, irreducible static, it just freezes.
It gets stuck.
To the algorithm, every single frame of static is mathematically new.
Right. It can never successfully predict the next arrangement of black and white pixels.
So instead of exploring the rest of the environment, it just sits in front of the TV forever, gorging on an infinite loop of unpredictable data.
It's harvesting a localized infinite reward.
That's so funny. It just found a hack.
It did. But the core technical failure in both of these historical approaches is that they fail to distinguish between two completely different types of uncertainty.
Okay, what are they?
First, there is epistemic uncertainty, which basically means, I don't know how this works yet, but I can learn it.
Like learning the layout of a new house.
Exactly. And then there is aleatoric uncertainty, which is, this is fundamentally random, like a dice roll, and no amount of learning will ever allow me to predict it.
Like the TV static.
Right. Older models pre-commit to a single uncertainty structure by design. They either minimize all uncertainty, leading to the dark room, or they maximize all uncertainty, leading to the noisy TV.
Now, I've seen some recent papers try to fix this by kind of mashing the two approaches together, like these adaptive approaches, right? S-adapt or mixture of surprises.
Yeah, those are out there.
Or basically just install a toggle switch in the AI.
Yes, they use what's called a bandit system. It's essentially an algorithmic manager that sits on top of the AI and manually flips a switch.
Oh, interesting.
It looks at the environment and decides, okay, we're in a static maze, switch the reward function to maximize surprise. Or we're in a chaotic room, switch it to minimize surprise.
But the paper we are looking at today argues that these bandit systems are fundamentally flawed band-aids.
They really are.
Because if an algorithm is constantly toggling between minimizing and maximizing its core drive, you introduce what the researchers call non-stationarity, which means the fundamental rules of what the AI finds rewarding are shifting independently of the actual environment it's exploring.
The goalposts keep moving.
Exactly.
Imagine trying to play a game where the rules for scoring points randomly invert every few minutes, but nobody tells you when or why.
That would be a nightmare.
You'd never develop a coherent long-term strategy. And that shifting creates incredibly unstable learning dynamics for an AI.
Which brings us to the actual breakthrough of this paper. The researchers proposed this unified framework called PRIME.
PRIME, yes.
It stands for Principled Direction-Free Intrinsic Motivation through Model-Free Epistemic-Free Energy Estimators.
Which is quite a mouthful.
A huge mouthful.
Yeah.
We are absolutely going to translate that for you, but the most important word in that dense acronym is direction-free.
That's the key.
PRIME does not use a toggle switch.
No bandit systems.
Right. It doesn't jump back and forth between hiding and seeking. It operates on a single, unified mathematical rule that naturally adapts to any environment.
And what's fascinating here is the engine of that rule. It's a concept called parameter information gain.
Okay, let's break that down.
In plain English, the AI is programmed to seek out the expected surprise of the next state, minus the irreducible aleatoric noise of that state.
Wait, so it wants to be surprised, but it actively subtracts the static on the TV from its calculations?
Yes. By seeking the expected surprise minus the irreducible noise, the agent is mathematically driven to seek out exactly the kind of surprise that its own internal model can eventually explain away.
All right.
It is specifically hunting for epistemic novelty. the stuff it can learn.
Okay, so let's say the AI walks into a room it has never seen before.
Right. Its internal model can't predict the layout, so the novelty term in its math equation is huge.
Because it's all epistemic.
Exactly. The agent actively explores and maximizes surprise to gather data, but as it walks around, it starts to learn the dimensions of the room. Its internal model updates.
It builds a map.
Yes. And as the room becomes understood, that epistemic novelty term essentially vanishes to zero.
Okay, wait, I have to push back here. If the novelty term drops to zero the moment the AI learns the environment, why doesn't the AI just stop moving?
That's a great question.
Like, if it has exhausted all the learnable information in the room, it seems like it would just fall right back into the darkroom trap.
And that is the exact vulnerability you would expect. It's where the second half of Prime's architecture is so crucial.
Okay.
The researchers built in what they call an aleatoric penalty.
An aleatoric penalty.
Right. Once the epistemic value, the learning value of an area drops to zero, the novelty drive is no longer the dominating force in the equation.
So what takes over?
The only remaining option enforced by the math is to minimize this aleatoric penalty. The agent actively begins to prefer actions that lead to next states with lower expected transition entropy.
So it shifts from exploring to seeking stability.
Exactly. It starts preferring actions that lead to lower variance, more predictable states.
Without a toggle switch.
That's the beauty of it. It naturally transitions to minimizing surprise, all without a human or a bandit system ever stepping in to flip a switch.
The math just flows naturally from, I need to learn to I have learned, now I need to maintain stability.
Yes.
It's literally using boredom as a mathematical tool. It explores until it gets bored of the known, and it avoids the purely random because it recognizes it can never be mastered.
Precisely.
But, theory on paper is one thing. I want to look at how this actually performed in the simulated lab tests.
The simulations are really telling.
Yeah, because the researchers set up two highly specific didactic environments to test Prime against the older methods. They used these 10 by 10 grids with a hard limit of 100 steps per episode.
Right, they needed to isolate these extreme failure modes we've been talking about.
So the first environment was a maze.
A classic, low-entropy, highly deterministic environment. It's a static grid with walls and a single exit. There is no random noise.
And when you look at the actual behavioral data for the older surprise minimizing method, SmearOL, it's almost comical.
It really is.
SmearOL had a 1% reach rate for the exit. Because it was so terrified of surprise, it would take maybe one step, register, that moving its digital body caused the pixels in its vision to change, and it would just halt.
Yeah, it pressed itself against a wall and refused to move.
Just so its sensory input would remain perfectly static.
It failed the task completely because the task required exploring a quiet space.
But Prime.
Prime, however, hit a 79% peak reach rate.
Wow.
It walked into the maze, realized the corridors represented epistemic uncertainty, things it didn't know but could learn, and it systematically mapped the space until it found the exit.
Okay, then they tested the exact opposite extreme, an environment called butterflies.
The high entropy environment.
Yeah, the grid is populated with these randomly moving butterflies, and the agent gets points for catching them. But the movement of those butterflies is mathematically irreducible noise.
This is the noisy TV problem made physical.
Exactly. If the agent chases the butterflies, simply because their movement is unpredictable, it will just run in circles chasing pure noise and fail to efficiently clear the room.
But Prime successfully caught an average of 3.47 butterflies per episode.
It actively pursued them.
Yes.
It actually outperformed a baseline position-only comparator policy that only scored 2.45. But wait, why did it hunt them down? If the butterflies are irreducible noise, shouldn't Prime just ignore them the way it ignores the noisy TV?
That is a brilliant nuance in how the environment reacts to the agent.
Okay.
Yes, the butterflies are irreducible noise, but in this specific environment, catching a butterfly actually removes it from the grid.
Oh.
By actively pursuing and capturing the source of the noise, the agent is effectively cleaning up its environment.
It's lowering the noise of the room.
Exactly. It lowers the overall irreducible noise. The math naturally leads to an outcome where the agent decides the most efficient way to achieve a stable, low-variance state is to just eliminate the sources of random chaos.
That is incredible.
Yeah.
And it achieved this high-level success in both the deterministic maze and the stochastic butterfly room using the exact same intrinsic objective.
The exact
I
same.
looked at the methodology, and they used identical hyperparameter configurations across the board, like no manual tuning behind the scenes.
That is the most rigorous proof of their concept. The algorithm simply adapted its behavior based purely on the mathematical reality of its surroundings.
Here's where it gets really interesting, though, because this behavior, it mirrors biological life in a way that is hard to ignore.
Oh, absolutely.
The paper leans on the free energy principle, which Carl Fiston originally developed to explain biological systems. Living organisms don't just passively seek out dark, quiet caves to minimize surprise.
No, they'd starve.
Right. They transiently raise their own exposure to surprise. They explore the forest. They hunt. They take risks specifically in order to gather information. And they do that so they can lower their surprise long term. Like you explore the territory so you know where the predators are, which makes your continued existence much more predictable.
Prime is essentially executing the free energy principle computationally. It derives surprise-minimizing behavior natively from a primary information-seeking drive.
That's amazing.
It bridges the gap between computational reinforcement learning and biological active inference.
But, to truly appreciate how this functions in real time, we have to look under the hood. Like, how does a computer calculate what is random versus what is learnable without explicitly rendering a massive simulation of the entire world and just, like, crashing its own processor?
Right, because Prime is model-free.
Meaning it isn't trying to generate a frame-by-frame prediction of the whole grid.
Exactly. Traditional model-based AI tries to build an explicit next-state predictor. It tries to hold the entire world in its memory to guess what happens next.
Which takes a lot of power.
That is incredibly computationally expensive. Prime bypasses this by using what are called pseudo-counts to track its epistemic term.
Pseudo-counts.
Yeah, it essentially keeps a sophisticated mathematical tally of how frequently it has encountered specific states rather than trying to draw a whole picture of them.
But the mechanism that really holds this all together is what the researchers call the statistics window.
This is a vital piece of the architecture.
I want to make sure we understand this because it seems to be the core reason the AI doesn't just spiral into chaos. So what does this all mean? Think of this like a university student's curriculum. Okay. If a student tries to rewrite their entire syllabus every single night based on the one new thing they learned that day, they would be paralyzed by constant restructuring.
They'd never actually finish a project.
Never. So by implementing a statistics window, the programmers are essentially freezing the curriculum for a set period. You lock in the learning goals, you tell the AI, just master this specific set of parameters based on your current knowledge, and only after that window closes do you update the syllabus.
If we connect this to the bigger picture, that is a highly accurate way to visualize it. In mathematical terms, freezing those windows yields a stationary Bellman operator.
Okay, you're going to have to explain that one.
A Bellman equation is just the formula the AI uses to calculate the value of its future rewards. When we say the operator becomes stationary, it just means the target the AI is aiming for is locked in place.
Like the frozen syllabus.
Exactly. And this guarantees a property called a gamma contraction within the window.
Let's translate gamma contraction so you don't lose anyone.
A gamma contraction simply guarantees that with every step the AI takes, the mathematical distance between its current guess and the true correct answer is getting smaller.
It's contracting.
It is contracting. If your target is constantly moving, which is what happens in those older bandit toggle switch systems.
The goalposts are shifting.
Right. You can never guarantee that your errors are shrinking. You might actually be getting further away from the optimal behavior. By freezing the targets, Prime guarantees mathematical stability. The AI can actually finish learning a concept before the environment demands it learn something else.
Wow. I looked at the ablation studies they ran, where they intentionally turn off specific parts of the code to see what breaks.
To stress test.
Yeah, and they highlighted a mechanism called the K=5 statistics heads. Why is that specific ensemble setup, like the linchpin of this process?
Well, the statistics heads are essentially subbrains within the AI's neural network.
Okay.
In this case, there are 5 of them. They all look at the exact same data, but they process it slightly differently. The AI measures novelty or surprise by looking at how much these 5 subbrains disagree with each other.
Oh, they take a vote?
Basically, yeah. If all 5 subbrains output the exact same prediction, the variance is 0. The AI knows it completely understands this area.
Makes sense.
But if the 5 heads output wildly different predictions, the crosshead variance is high. The AI realizes, oh, I'm in an unknown area I need to explore.
So what happened when they ablated it?
When they reduced it down to just one statistics head, the AI's performance plummeted.
Because it had nothing to compare its own internal assumptions against.
Exactly. It needs that internal disagreement to gauge its own uncertainty.
There was another fascinating mechanism they tested called the short horizon gate. It seems like a tiny piece of code, but turning it off caused noticeable drops in how efficiently the agent navigated.
Yeah, the short horizon gate acts almost like a mathematical courage parameter.
Courage parameter. Yeah.
Remember the aleatoric penalty we discussed?
The mechanism that punishes the agent for walking into noisy, unpredictable areas.
Right. Well, sometimes the AI has to walk through a genuinely noisy hallway just to get to a highly informative, unexplored room.
Oh, I see.
If the aleatoric penalty is always fully active, the AI might get scared by the noisy hallway and turn back, never reaching the new room.
It gets too risk-averse.
Exactly. So the short horizon gate temporarily suppresses that penalty if it calculates that an informative near-term future is just a few steps away.
That is so cool. It protects the AI's ability to take calculated risks.
Yes, it's an incredibly finely tuned system.
It really is. I mean, to synthesize what we've unpacked for you today, we are looking at a fundamental evolution in how autonomous agents process reality.
Without a doubt.
For years, we were stuck choosing between algorithms that were, terrified of the dark or algorithms that were addicted to the static of noisy television.
We had to choose our failure mode.
Right. But by relying on parameter information, gain-seeking surprise, while mathematically subtracting irreducible noise, Prime solves both failures simultaneously.
It's so elegant.
It gives us a dynamically curious AI that natively transitions from exploring the unknown to mastering its environment and seeking stability.
And like I said, the elegance of the math cannot be overstated. It is a massive step toward general-purpose agents that can be dropped into the real world without constant human supervision.
Think about how Prime behaves, specifically how it immediately recognizes the random butterfly movements as irreducible noise and mathematically ignores them because they offer no epistemic value.
Yeah.
It makes me think about what happens when these agents leave the simulated grids. We're building these mathematically perfect, curious machines, and eventually they are going to be deployed into our digital ecosystems.
This raises an important question, actually. They'll be deployed into the internet, essentially.
Right. And if you look at human digital culture right now, it is largely driven by social media algorithms that are specifically optimized to act exactly like noisy TVs.
That's a scary thought.
They generate endless stochastic novelty, infinite feeds of random, emotionally spiking content designed specifically to capture our attention. We fall for the noisy TV trap every single day.
The modern internet is basically a landscape of manufactured, irreducible, aleatoric noise.
Exactly. So imagine we boot up the ultimate autonomous prime-driven AI. We connect it to the internet, expecting it to boldly explore human culture.
And learn all about us.
Right. And its first act of intelligence, driven entirely by this flawless mathematical logic, is to calculate that our entire attention economy has absolutely zero actual epistemic value.
Yes.
The ultimate curious machine might log onto our internet, realize that our feeds are just static, and simply choose to unplug.
It would just look away.
It's a profound realization that a purely logical machine might immediately reject the very environment we spend most of our lives staring at. Something for you to think about next time you find yourself endlessly scrolling through the noise. Thanks for joining us on this deep dive into the mechanics of machine curiosity, and keep questioning the algorithms that are learning about you.